Section 7.3, double angle, half angle, and reduction formulas. In this section, we're going to take a look at three families of trig identities. We'll start with the double angle identity. The first double angle identity is for a sine, and it states that sine of 2 theta equals 2 sine theta cosine theta. To verify this identity, we're going to start by rewriting the left-hand side. So far, the only identities that allow us to change the input of a trig function are the even-odd properties, cofunction identities, and the sum and difference identities. Since we don't have a negative sign inside our sine function, we won't use the even-odd identities. Since we're not trying to rewrite the sine as cosine, we're not going to use the cofunction identities. But 2 theta is just a way of writing theta plus theta. So by writing the 2 theta as theta plus theta, now we're able to use the sum formula for sine. Sine theta, cosine theta, plus cosine theta, sine theta, the two terms are alike even though the order of sine and cosine is different. So we can add the two terms together, giving us 2 sine theta cosine theta, which is our right-hand side. And we can do something similar for tangent. To verify the double angle identity for tangent, we'll start with the left-hand side, tangent of 2 theta, write the 2 theta as theta plus theta. Then we can use the sum formula for tangent, and we have tangent theta plus tangent theta all over 1 minus tangent theta times tangent theta. In the numerator, tangent theta plus tangent theta is 2 tangent theta. In the denominator, tangent theta times tangent theta is tangent squared theta, which will leave our right-hand side. Now, the reason why we skipped the cosine 2 theta is because there's actually 3 identities for cosine 2 theta. We're going to go ahead and verify all 3. We're going to first verify the first, that cosine 2 theta equals cosine squared theta minus sine squared theta. So we'll start with our left-hand side, and we'll use the same trick we've done before. We'll write the 2 theta as theta plus theta, and then use the sum identity for cosine. And when we do, we get cosine theta minus sine theta, and we get cosine squared theta minus sine squared theta. Now, for the other 2 versions of the cosine 2 theta, which is 1 minus 2 sine squared theta and 2 cosine squared theta, they can be derived by using the Pythagorean identity on the cosine squared theta minus sine squared theta. Recall the Pythagorean identity is sine squared theta plus cosine squared theta equals 1. Well, we can solve for sine squared or cosine squared within the Pythagorean identity, and we get sine squared equals 1 minus cosine squared, or cosine squared equals 1 minus sine squared. If we apply the middle version of the Pythagorean identity, we can replace the sine squared with 1 minus cosine squared, distribute in the negative 1, and combine like terms. And there we have the third version, that cosine 2 theta also equals 2 cosine squared theta minus 1. If we apply the cosine squared theta equals 1 minus sine squared theta, we can rewrite the cosine squared theta minus sine squared theta as 1 minus sine squared theta minus sine squared theta, which equals 1 minus 2 sine squared theta, which establishes the middle version, that cosine 2 theta also equals 1 minus 2 sine squared theta. Next, we're given that theta is in quadrant 3, and that tangent theta equals 4 over 3. What we're going to do is find sine 2 theta, cosine 2 theta, and tangent 2 theta. If we think about the fact that we're trying to find sine 2 theta, cosine 2 theta, and tangent 2 theta, the 2 thetas tell us we should use the double angle identities. Applying the double angle formula to the sine 2 theta, we have that sine 2 theta equals 2 sine theta cosine theta. The problem is I only know tangent theta. So to figure out my sine 2 theta, according to the formula, I do also need to know sine theta and cosine theta. So how do we find sine and cosine just from us being given tangent theta? Well, this is similar to exercises we've done before, where we were given one trig function and we found all the others. What we're going to do is try to find another trig function and just see where it goes. It may not be sine, it may not be cosine. Unfortunately, I can't just say that sine theta equals 4 and cosine theta equals 3, trying to think we can use the quotient identity. Sine theta cannot be 4, cosine theta cannot be 3, 4 and 3 are bigger than 1, sine and cosine cannot take on values bigger than 1. If we think about our identities, specifically the Pythagorean, we know that secant squared theta equals 1 plus tangent squared theta. So if we plug in the 4 over 3 for tangent theta, we get that secant squared theta equals 1 plus 4 over 3 squared, which means secant squared theta equals 25 over 9. Then we can square root both sides, and when we square root both sides, we get that secant theta equals plus or minus 5 over 3. Because we know that theta is in quadrant 3, and tangent and cotangent are the only 2 trig functions that are positive in quadrant 3, then secant theta must be negative. So secant theta is negative 5 over 3. Since secant is the reciprocal of cosine, that means cosine theta is negative 3 over 5, which means we have the cosine theta. Now we just need sine theta. Using the quotient identity, we know that tangent theta is sine theta over cosine theta. Or in other words, sine theta is cosine theta times tangent theta, which is negative 3/5 times 4/3, which is negative 4/5. So now we've just found the value of our sine theta. So we can plug in our values, and we get that sine 2 theta equals 2 times negative 4 over 5 times negative 3 over 5, which is 24 over 25. Next up, cosine of 2 theta. Cosine of 2 theta has 3 different identities. Depending on the given information, one is more convenient than the other. Let's say we were doing this problem from scratch, where I didn't already have the value of cosine and sine. I would still need to figure out at least one of those values, because one option is I could use the 1 minus 2 sine squared theta version, or I can use the 2 cosine squared theta minus 1 version. So thanks to those variations, I just need either sine or cosine. I don't necessarily need both. Going back to the idea of doing this by scratch, the first trig function I found was cosine theta. So if I want to do this the most efficient way, if I were doing this from the very beginning, I would use the 2 cosine squared theta minus 1 as soon as I found that cosine theta. And we get that cosine 2 theta equals 2 times negative 3 over 5 squared minus 1, which equals negative 7 over 25. Since we do have sine and cosine, try at home. Check to see that you still get negative 7 over 25 no matter which version you use. Lastly, for tangent 2 theta, the formula for tangent 2 theta is 2 tangent theta all over 1 minus tangent squared theta. So with the given information, this one we could actually find the quickest. Because we were already given tangent theta, we can just go ahead and plug in our values, and then we can go ahead and evaluate. And we get negative 24 over 7. Next, we're going to try to write the following expressions as a single trig expression. Starting up, we're going to rewrite 2 sine 16 degrees cosine 16 degrees. Now, this is an exercise where we have to really be familiar with our identities. We only have one identity where we're multiplying sine and cosine together, where the angles are specifically the same. That is specifically the double angle identity for sine. The double angle identity for sine, when reversed, is 2 sine theta cosine theta equals sine 2 theta. Here, the 2 sine 16 degrees cosine 16 degrees is exactly the left-hand side I just put down, where theta would be 16. So 2 sine 16 degrees cosine 16 degrees would equal sine of 2 times 16 degrees, which is sine of 32 degrees. So here, we've written our expression as a single trig function. Next up, we're going to simplify cosine squared pi over 6 minus sine squared pi over 6. We have to be very careful with what identity we pick here. Because we see the sine squared and cosine squared, it might be very tempting to use the Pythagorean identity. But if we look very carefully, notice how we're subtracting cosine squared and sine squared. What other identity involves us subtracting cosine squared and sine squared where the angles are the same? That would be our first double angle identity for cosine. That cosine squared theta minus sine squared theta equals cosine 2 theta. Here in our expression, pi over 16 would be theta, and we get that cosine squared pi over 16 minus sine squared pi over 16 equals cosine of 2 times pi over 16, which is cosine of pi over 8. Next, we're going to simplify cosine squared 5y minus sine squared 5y. Very similar to the last problem, we're subtracting cosine squared and sine squared. So we should try to apply the first cosine double angle formula. Here, 5y would be our theta, and we get cosine of 2 times 5y, which simplifies to cosine of 10y. Next up, we'll simplify 2 of sine of 6x cosine of 6x. Here, since I'm multiplying sine and cosine together and the angles are the same, we want to think about the double angle formula for sine. Here, 6x would be theta, so 2 sine of 6x cosine of 6x will equal sine of 2 times 6x, which equals sine of 12x. Now we're going to verify that 1 plus sine 2 theta equals sine theta plus cosine theta squared. Just like what we've discussed in previous sections, we want to start by simplifying the ugliest side. Here, the right-hand side appears to be the ugliest side. So we'll start by trying to simplify the sine theta squared plus cosine theta squared. Using the left-hand side as inspiration, notice that the left-hand side is not a square of a binomial. So the first thing we should try to do is square our binomial here. And when we do, we get sine squared theta plus 2 sine theta cosine theta plus cosine squared theta. This is where it's really important to know our basic identities. Notice how we have sine squared theta and cosine squared theta being added together. And keep in mind, order of addition doesn't matter. Thanks to the Pythagorean identity, we know that this sum is 1. So we can simplify our right-hand side down to 1 plus 2 sine theta cosine theta. Now let's look at the left-hand side for inspiration. I'm happy with the 1 that we have present that we got through the Pythagorean identity. But if we look at the sine 2 theta on the left-hand side, notice that the input is 2 theta. So how can I rewrite the 2 sine theta cosine theta as sine 2 theta? Well, that would lead us to want to use the double angle identity, just like what we did in the last example. The double angle identity tells us that 2 sine theta times cosine theta is sine 2 theta. So our right-hand side does simplify to 1 plus sine 2 theta, which is our left-hand side. Next, we're going to verify that cosine to the 4th theta minus sine to the 4th theta equals cosine 2 theta. So which side here would be the ugliest, the left or the right? Here, it would be the left-hand side. So we're going to try to simplify the cosine to the 4th theta minus sine to the 4th theta. Now, how do we get from cosine to the 4th theta minus sine to the 4th theta equals cosine of 2 theta? But we don't have an immediate identity for cosine to the 4th or sine to the 4th. But let's try to factor this, because if we can factor this and make the power smaller, perhaps we can use other identities like Pythagorean or the double angle identities. Now, keep in mind that cosine to the 4th theta minus sine to the 4th theta is a difference of squares. So it would factor to cosine squared theta minus sine squared theta times cosine squared theta plus sine squared theta. Now, we could factor a little bit farther, but we have identities that involve cosine squared theta and sine squared theta. If we look at the first, we have cosine squared theta minus sine squared theta. By the double angle identity for cosine, we know that's cosine 2 theta, which is precisely what we want to see in our right-hand side. As for the cosine squared theta plus sine squared theta, by Pythagorean identity, we know that's 1. Anything times itself is 1, so we're able to simplify our left-hand side to cosine of 2 theta, which is our right-hand side. The next family of formulas we're going to talk about are the power reduction formulas. These formulas are not necessarily useful for computation, but they are very useful in calculus because they take expressions such as sine squared theta, cosine squared theta, and tangent squared theta, which really don't behave nicely in an operation called integration, and allow us to rewrite them with smaller powers that make them a lot easier to integrate in calculus. These identities all stem from the different variations of the cosine 2 theta identities. If we recall from the cosine 2 theta identities, cosine 2 theta can either be written as 1 minus 2 sine squared theta, or it can be written as 2 cosine squared theta minus 1. If we manipulate these two variations and solve for the trig function that's being squared, in the first, we would subtract 1, then divide by -2. To make it look a little nicer, we can multiply top and bottom by -1, and we obtain that sine squared theta equals 1 minus cosine squared theta. Through a similar process of adding 1 and dividing by 2, we obtain that cosine squared theta equals 1 plus cosine squared theta all over 2. As for the tangent squared, recall from the quotient identity, tangent squared theta equals sine squared theta over cosine squared theta. Since we've already derived the power reduction formulas for sine squared and cosine squared, we can plug them into place, multiply top and bottom by 2, and we get the right-hand side, 1 minus cosine 2 theta over 1 plus cosine 2 theta for tangent squared theta. We're going to write an equivalent expression not containing powers greater than 1 of sine to the 4th x. This is a very common exercise in calculus because sine to the 4x is not really the nicest function to perform an operation called integration on. So what we try to do is rewrite our sine to the 4th x so that way it has no power greater than 1, and it makes it a lot easier to handle in this operation called integration. Thanks to the power reduction formula, we can rewrite sine squared of x. Since we have the 4th power, we can rewrite the sine to the 4th x as sine squared x quantity squared. Then we can apply the power reduction formula for sine, and we obtain 1 minus cosine of 2x all over 2 quantity squared. We're going to square the numerator and the denominator, as we do with fractions. When we square the numerator, we get 1 minus 2 cosine 2x plus cosine squared of 2x. When we square the denominator, we get 4. Now let's go ahead, just to make it a little bit easier to work with, we're going to divide each term in our numerator by 4. And when we do, we get 1/4 minus 1/2 cosine of 2x plus 1/4 of cosine squared 2x. The reason why we're writing it as 1/4 of cosine squared 2x as opposed to cosine squared 2x over 4 is because it's going to make it easier for us to use our power reduction formula again. Since I have a power of cosine greater than 1, I have to apply my power reduction formula again. However, when I apply my power reduction formula again, keep in mind our input to the cosine squared is 2x. So when I apply my power reduction formula, theta is 2x this time. So cosine squared of 2x becomes 1 plus cosine of 2 times 2x all over 2. Keep in mind dividing by 2 is the same as multiplying by 1/2, and 2 times 2 is 4. So we can rewrite our last term as 1/4 times 1/2 times 1 plus cosine 4x. The 1/4 and the 1/2 we can multiply together. Then we can distribute into 1/8. Lastly, we can collect our like terms by adding the 1/4 and the 1/8. So after applying our power reduction formulas a few times, we get cosine to the 4th x equals 3 over 8 minus 1/2 cosine 2x plus 1 over 8 cosine 4x. Notice that in our final answer, we have no powers greater than 1. Therefore, I can't use the power reduction formula, and I've satisfied the instructions of the problem. Now we're going to verify the following identity. Sine cubed of 2x equals 1/2 of sine of 2x times 1 minus cosine of 4x. Now, at first glance, it may be tempting to say the right-hand side is the uglier side. The issue is I have that cubed on the left-hand side. And typically with higher powers, they make the trig functions a little harder to work with. While the left-hand side may look a lot more simpler and visually appealing, there's a lot more simpler work we can do thanks to power reduction. So we're going to start off with the sine cubed of 2x. Now, just like in past problems, we're going to take inspiration by the right-hand side to determine what to do next. One thing to note, on our right-hand side, we have a sine of 2x. Sine of 2x is the base of my left-hand side, so using exponent properties, we can pull away a sine of 2x and rewrite our sine cubed as sine times sine squared. And remember, the input will be 2x. Now again, looking to the right-hand side, notice how we have no powers greater than 1. So with the sine squared of 2x, I'm going to apply the power reduction formula, just like what we did in the previous problem. So sine squared of 2x becomes 1 minus cosine of 2 times 2x when we apply the power reduction formula for sine. And we get 1 minus cosine of 4x all over 2. Now, if we take a look at our right-hand side again, we're happy to see that 1 minus cosine of 4x. Notice that we do have a 1/2 in front, and keep in mind dividing by 1/2 is the same as multiplying by 1/2. So now we're just going to simply rewrite our form. Instead of writing divided by 1/2, we'll write times 1/2, bring it out to the front, because multiplication is commutative. Since we're multiplying by the expression 1 minus cosine of 4x, we want to keep that 1 minus cosine of 4x in parentheses, and there's our right-hand side, verifying the identity. Most of the use of the power reduction formula does come into play in calculus. However, it can be used to help us derive another formula that is very useful for computing trig functions at angles not necessarily on the unit circle. And these are the half-angle formulas. Through the power reduction formula of sine, we have that sine squared x equals 1 minus cosine 2x all over 2. If we set x equal to theta over 2, our left-hand side becomes sine squared theta over 2. Our right-hand side becomes 1 minus cosine of 2 times theta over 2, which is just theta, all over 2. If we take the square root of both sides, we get sine theta over 2 equals plus or minus the square root of 1 minus cosine theta over 2. And remember, since we had to take the square root of both sides, we have to remember to include that plus or minus. Now, this would seem to indicate that sine theta over 2 could have two different values, one positive, one negative. However, sine is a function, so no matter what we input, we should only get one answer. What the plus or minus tells us in this scenario is we need to think about whether sine theta over 2 will be positive or negative based off of what quadrant theta over 2 is in and our sine rules for our trig functions. And we also can derive a similar formula for cosine theta over 2. Cosine theta over 2 equals plus or minus the square root of 1 plus cosine theta over 2. Again, the plus or minus is to be determined by us based off of what quadrant theta over 2 is in. Tangent actually has 3 different versions of its half-angle formula. The first is plus or minus the square root of 1 minus cosine theta all over 1 plus cosine theta. This comes directly from the power reduction formula of tangent, but we do have 2 other variations, which are actually quite nice because they don't have the plus or minus. These variations come from using conjugates to rewrite what's inside of the square root. If we multiply top and bottom inside of the square root by 1 minus cosine theta, in the denominator, we get 1 minus cosine squared theta. In the numerator, we're going to leave it as 1 minus cosine theta squared. And that's because we're multiplying these same numbers together. And the reason why we want to keep the square is because we want to get rid of the square root. 1 minus cosine squared theta, we know is sine squared theta from the Pythagorean identities. Now from here, how do we get rid of the square and the square root? Well, we have to be a little careful with signs. Technically speaking, when you take the square root of x squared, we want to say that it equals x. But that's not true if x is negative. In actuality, if we're considering any possible value of x, positive or negative, it's actually equal to the absolute value of x. So when we cancel the square and the square root, we're left with plus or minus the absolute value of 1 minus cosine theta all over sine theta. If we think about the range of cosine theta, we know that cosine theta is less than or equal to 1, which means 1 minus cosine theta can never be negative. And the absolute value of something that's never negative is itself. So we can drop those absolute values around the 1 minus cosine theta. Now what's interesting is the absolute value of sine theta. The absolute value of sine theta could either be positive sine theta or negative sine theta. But we already have this plus or minus here. It turns out, due to where sine theta is positive, it will correspond to where tangent theta over 2 is also positive. And wherever sine theta is negative, tangent theta over 2 will also be negative. As an exercise, consider the cases where sine theta is positive and negative, and convince yourself that tangent theta over 2 will also be positive or negative. So for that reason, we can drop the plus or minus and the absolute value at the same time, because the sine of sine theta will coincide with the sine of tangent theta over 2. Just like with the sum and difference formulas we learned before, one of the great uses of the half-angle identities is it can allow us to evaluate trig functions at angles that are not on the unit circle. For example, sine of pi over 8. We don't see pi over 8 on the unit circle, but we do know that pi over 8 is just half of pi over 4. So sine pi over 8 equals sine of pi over 4 over 2. Then we can apply the half-angle formula, and we get that sine of pi over 8 equals plus or minus the square root of 1 minus cosine pi over 4 all over 2. And we can find the exact value of cosine pi over 4 on the unit circle. Now, before we do that, though, let's think about the sign of our answer. Should it be positive or negative? Pi over 8 is an angle in quadrant 1. Sine should be positive whenever we're trying to evaluate at an angle in quadrant 1. So we're going to keep the plus sign and drop the negative sign. Now we can evaluate the cosine pi over 4. From the unit circle, we know that cosine pi over 4 is root 2 over 2. To help simplify the complex fraction, we'll multiply top and bottom by 2, and we get the square root of 2 minus root 2 all over 4. Since 4 is a perfect square, let's go ahead and take the square root of the denominator, and we get the exact value of sine of pi over 8 equals the square root of 2 minus root 2 all over 2. Next, we're going to find the exact value of tangent of 112.5 degrees. Just like in our last problem, 112.5 degrees does not appear on the unit circle, but 225 degrees does appear on the unit circle. So now we can apply the half-angle formula for tangent. Now there are 3 different versions of the half-angle formula for tangent. You can pick either version you want. It is up to you. Here, because I really want to emphasize the picking of the plus or minus, we're going to use the first variation. Now, which sign should we keep, the plus or the minus? 112.5 is in quadrant 2. In quadrant 2, tangent is supposed to be negative. So here, we're going to keep the negative sign. Now evaluate cosine. Cosine of 225 is negative root 2 over 2. To clear out the complex fractions, we'll multiply top and bottom by 2 and clean up the signs at the same time, and we get negative square root of 2 plus root 2 over 2 minus root 2. We'll go ahead and rationalize the denominator within the radical, multiply top and bottom by the 2 plus root 2. In the top, we're not going to FOIL it because I am multiplying the same thing with itself, so that would become 2 plus root 2 squared. In the denominator, when I FOIL it out, we're going to get 4 minus 2. When we square root top and bottom, because the 2 plus root 2 is a positive value, that will simplify to 2 plus root 2, while the denominator simplifies to root 2. We can rationalize the denominator again, and we get 2 root 2 plus 2 over 2, reduce again, and we get negative root 2 plus 1, which if you feel like distributing in the negative, we get negative root 2 minus 1. Now, this was pretty long with a lot of rationalizing, The reason why I picked this method was just so that way I can emphasize the choice between the plus or the minus. However, the most efficient way to go about this is instead, we could use one of the variations without the radical and without the plus or minus. Specifically, let's go ahead and use the third variation. Now, the drawback is I do have to evaluate two different trig functions, but since the angle is the same, I'm still looking at the same point. Now, both cosine 225 and sine 225 degrees will be negative root 2 over 2. In order to help us clear the denominators, we are going to multiply top and bottom first by negative 2. And this is because I do want to make my denominator positive. But thinking ahead, I do also need to rationalize that root 2 in the denominator. So let's go ahead and multiply top and bottom by root 2. In the numerator, we'll distribute. When we distribute in the numerator, we get negative 2 root 2 over 2. In the denominator, when we multiply that out, we're going to get 2. And then we can reduce. We get negative root 2 minus 1, just like what we did in our first method. So given that 3 pi over 2 is less than theta, less than 2 pi, and that tangent theta equals negative 12 over 13, we're going to find the exact value of sine theta over 2, cosine theta over 2, and tangent theta over 2. To start, let's take a look at the formulas we should apply for our trig functions at theta over 2. Sine and cosine only have one version. That is, sine theta over 2 equals plus or minus the square root of 1 minus cosine theta over 2, and cosine theta over 2 equals plus or minus the square root of 1 plus cosine theta over 2. Now for tangent, we actually have three options. We could either use the one with the square root, or we can use the one that depends on sine and cosine. Since the sine and cosine half-angle formulas only depend on cosine theta, the quickest approach would be to use the version that only depends on cosine theta. So now if we can figure out the value of cosine theta, we can easily figure out our half-angles. Now, we are only given tangent theta equals negative 12 over 13. Just like in our previous problem, we can use the fact that tangent theta equals negative 12 over 13 to try to figure out the value of any of our trig functions. Using the Pythagorean identity, specifically the version 1 plus tangent squared theta equals secant squared theta, we can plug in our value for tangent theta and proceed to solve for secant. After we plug in our tangent theta, we get 1 plus negative 12 over 13 squared equals secant squared theta. If we simplify the left-hand side, we get that secant squared theta equals 313 over 169, square root both sides, and we get that secant theta equals plus or minus root 31 over 13. Now we have to determine if we should use the plus or the minus. We're told that theta is between 3 pi over 2 and 2 pi. This tells us that theta is in quadrant 4. The only trig functions that are positive in quadrant 4 are cosine and its reciprocal secant. So secant theta is going to equal positive root 313 over 13. So secant theta will equal root 313 over 13. Cosine is the reciprocal of secant. So cosine theta would equal 13 over root 313, or 13 root 313 over 313 after rationalizing. Now that we have cosine theta, we need to figure out what the sign of our trig function should be. To figure out the sign of our trig functions, we need to figure out what quadrant theta over 2 is in. We're given that theta is between 3 pi over 2 and 2 pi, and we did use that prior to figure out the sign of cosine. We can also use this to figure out where theta over 2 will be located. Since we're interested in theta over 2, we're going to divide our inequality by 2, and we get that theta over 2 is between 3 pi over 4 and pi, which is located in quadrant 2. In quadrant 2, sine is positive, while the other two, cosine and tangent, will be negative. Now that we've identified the sign of our trig functions, let's go ahead and plug in our value for cosine into all three of them. Now with our value plugged in, we can simplify each one. For all three of them, to clear the complex fractions, we'll multiply the numerator and denominator inside of the radical by 313. Then we can go ahead and distribute. So we get that sine theta over 2 equals the square root of 313 minus 3 root 313 over 626. Cosine theta over 2 equals negative square root of 313 plus 13 root 313 all over 626, while tangent theta over 2 equals negative square root of 313 minus 13 root 313 all over 313 plus 13 root 313. As an exercise, practice finish rationalizing these expressions, but we do have the exact value now of sine theta over 2, cosine theta over 2, and tangent theta over 2, thanks to the given information.